Deposits of marine clay in Norway cover a total area of 40,000 square kilometres. Within this area, quick clay slides represent a serious problem, involving potential loss of lives and property. This documentary film presents the story of such a landslide. It contains unique pictures taken by two amateur photographers who happened to be at the scene. During the last glaciation, the northern hemisphere was more or less entirely covered by glaciers. In Scandinavia, the weight of an approximately 3,000-metre thick ice cap loaded the bedrock. During deglaciation, the sea transgressed in front of the retreating ice. About 11,000 years ago, the coasts of Norway were submitted to conditions similar to those in Spitsbergen and Greenland today. Melting water from the glaciers brought large amounts of suspended material into the fjords, where silt and clay were sedimented in the marine environment. Due to isostatic land uplift following the withdrawal of the glaciers, marine clay deposits rose above the water level. Such marine areas are shown with light green colour on the map, and can today be found up to surface elevations of 200 metres above present sea level. In Norway and Sweden, such areas constitute the best farming land and are among the most heavily populated areas. The bedrock surface is very undulated with outcropping hills and valleys filled to some extent with marine sediments. Rain and surface water subject the marine clay surface to erosion. With time, the top 5 metres have altered to a weathered crust of stiff fissured clay. At the same time, an upward flow of fresh groundwater from fissures in bedrock and through sand layers gradually leaches the salt out of the pore water of the marine sediments. In its natural undisturbed state, quick clay exhibits considerable strength. However, if the load becomes too heavy, as shown in this example, a failure takes place as the clay particle structure collapses, followed by remoulding of the clay. The most characteristic feature of a quick clay is the complete and drastic change of consistency by remoulding. Such extreme quick clay behaviour is encountered only when the salt concentration in the pore water drops below 1 gram per litre. To illustrate the important role of salt on the material properties, we can add a little ordinary table salt to the clay sample. When the salt goes back into the pore water, the salt ions alter the interaction between the minerals and the pore water. The remoulded strength increases dramatically, and the clay is no longer a liquid. Now let's look at the actual Rissa quick clay landslide. Rissa is situated close to the Trondheim fjord, northwest of the city of Trondheim. This air photo was taken a few years before the slide occurred. In the bottom right-hand corner, we see the marine water of the Trondheim fjord. On the left-hand side, we see a part of the freshwater lake Botnen. Between the fjord and the lake lies a fairly flat area of marine clay deposits, which for centuries has been farmland. This model of Rissa shows the locations of the small farms and of the connecting roads before the slide. Let's focus on this farm here, where the slide was initiated in April 1978. A new wing was to be added to the existing barn. The excavation for the 700 cubic metre basement took 2 days, and the soil masses were placed in a 2-metre high earthfill down by the shoreline of Lake Botnen. Just after the earthwork had been completed, a 70 to 90 metre length of the shoreline suddenly slid into the lake and disappeared. The load from the earthfill caused this initial failure. The slide developed retrogressively into the clay slope towards the right. An amateur photographer living in the area took up a position at the shoreline of Lake Botnen with his new 8mm movie camera, For the first time in history, we can actually see film of a quick clay landslide as it's happening. At this moment, the slide extended over an approximate 200-meter width. Successive minor sliding then took place continuously. The remolded soil masses moved down into the lake, creating small waves. Each new slide resulted in a complete liquefaction of the quick clay. You are witnessing on the screen the remolded quick clay at its natural water content. The debris literally splashed against the lower slide edge and moved like streaming water down the scarp and into the lake. In the background we can see the barn where the excavation was made. The retrogressive sliding process continued for about 40 minutes. The slide now extended over a 450-meter width and covered an area of 25 to 30,000 square meters. The slide area had now the shape of a long and narrow pit with a narrow gateway towards the lake. However, at this time, the real disaster started. Almost instantaneously, a large flake-type slide started, and our amateur photographer had to run for his life. In his own words, a wave of earth came rolling behind me. An eyewitness recounts, "Suddenly, an area of about 150 by 200 meters, including the old school building, sank down and moved monolithically towards the lake. The sliding mass didn't move through the existing slide scarp, but in the direction of the terrain slope. Most of the slide debris flowed into the lake, while some came to a stop in a compression zone close to the shoreline. A new large gateway had now been opened into the lake. The persons living on this farm behind the new steep slide scarp escaped with private cars just before the farm slid out. The persons living on this second farm were warned by their escaping neighbours and managed to get away just before their houses were taken by the slide. Back on safe ground, our amateur photographer again started his camera just in time to film a new large flake-type slide. The major sliding process was now completed. However, debris was still flowing into the lake. In a very short period of time, only some 5 minutes, the slide had propagated 1 kilometer along the mountainside. A second amateur photographer, who had heard about the landslide, had rushed for his camera and found a safe position on the hillside, from which he started filming the last portions of the slide activity below him. Sliding masses moved in the direction of the slope, hit the lower rim of the slide scarp, and were forced to flow to the right towards the lake. Just before the main flake slide started, about 40 persons were known to be within the affected area. At this moment, it was not clear how many had escaped. A rescue helicopter had arrived at the site. Small failures from the steep slide edges occurred continuously. In the inner part of the slide scarp, some sliding still took place. Here, a large clay block slid out, becoming more and more remolded. Suddenly, the quick clay completely liquefied. This helicopter panoramic view of the final slide scarp was taken in the evening, about 4 hours after the initial slide occurred. The first slide movement occurred in the direction of the terrain slopes from the hills in the back. The debris was then forced to move towards the lake to the left. This white house was taken by one of the many small slides which occurred during the first few days after the main slide. The neighbouring barn also ended up in the debris. Small brooks brought water into the slide area. The two main roads through the area were taken away by the main slide. From this farm, situated on an outcrop, many people watched the dreadful sliding activity. We now see the farm where the initial slide took place. When the masses from the major flake-type slide rushed into the lake, 2 or 3 large water waves were created. These waves propagated across the lake, a distance of 5 kilometers. At the other end, the waves flooded the small village of Leida, causing a great deal of damage. This amateur film, taken from a car window in Leida that same evening, shows damaged houses and cars and flooded basements. The sawmill and lumber yard, located close to the shoreline, were destroyed. This view shows the same sawmill the following morning. The first night after the major slide, 200 persons living close to the slide area were asked to evacuate. The local police were responsible for dealing with the situation. They were assisted by military personnel and civilians in the evacuation of cattle and clearing of the area. The slide area covered 330,000 square meters, and the slide volume was of the order of 5 to 6 million cubic meters. 7 farms and 5 single-family homes were taken by the slide or had to be abandoned for safety reasons. Of the 40 people who were within the area when the sliding started, only 1 was killed. Several farms and homes were situated close to the slide scarp. An important task was therefore to establish the margin of safety of these areas as soon as possible. Geotechnical investigations were carried out to map the extent of remaining quicklay. The site investigations included rotation soundings, vein tests, and undisturbed soil sampling. The undisturbed soil samples were taken by GeoNor's 54mm piston sampler. After field classification, The sample tubes were registered and put into boxes for transport to the laboratory. After transport of the sample tubes to the NGI laboratory in Oslo, the clay was extruded and prepared for various geotechnical tests. Routine investigations were first carried out, including fall cone tests as shown. Triaxial and simple shear tests provided more reliable strength parameters for the stability calculations. This is a typical geotechnical profile from Rissa. The blue line shows an average natural water content of about 30%. It should be noted that in the zone of quick clay, the liquid limit is 5 to 10% lower than the in situ water content. The green curve shows the vein shear strength and the red curve the remolded shear strength. The results of geotechnical analyses showed that stabilization works had to be carried out. The 15 to 20 meter high remaining terrace along the foot of the hillside contained quick clay and had to be taken down. For safety reasons, it was decided to do this by blasting. Holes 5 to 10 meters deep were drilled both from the top of the clay terrace and along the foot of the steep slope. 1 kilogram of dynamite was used per 100 cubic meters of clay. This blasting caused the remaining quick clay in the terraces to liquefy and run out into the slide area. These masses then eroded into the newly formed thin dry crust of the original slide bottom. After several rounds of blasting, the clay terrace was removed over its entire 1 kilometer length. The 5 to 10 meter high slopes at the opposite side could be stabilized by mechanical flattening. The clay was very soft and sensitive. The work was therefore carried out during the winter so that the necessary machines could be moved across the frozen top crust. Within 10 months after the slide, the entire zone surrounding the slide had been stabilized. The following year, work started on a new road, substituting the one taken by the slide. For a distance of about 1 kilometer, the hillside was blasted out for the new road. The families who suffered material losses recovered compensation partly from the National Disaster Agency and partly from their insurance companies. New dwellings, barns and outhouses were erected, and 4 years later, nearly all traces of the slide disaster had been wiped out. Once again, the slide areas being cultivated and crops harvested. The Rissa landslide gave the impulse to start a project of nationwide mapping of quick clay deposits. Hopefully, in the future, the results of this work will lead to a reduction in both the number and extent of quick clay disasters.